As I mentioned in the last video, so what we're going to have to do for these rigid body problems is to take the body sort of for here, perhaps that's part of a beam. Really probably should have drawn what you do to show you've cut it is just you draw a little line like that, but you'd usually do it in a small pen, a thin pen, or do it lightly with your pencil. So that just shows you that you've cut it. You draw something like that. In other words, what I'm saying is you've cut it for the drawing. So in reality, this would go on further, but you just cut it for the drawing. The same here. You should really have something like that. But that's not my point. What are we talking about? So you're going to have to draw free body diagrams. When you draw free body diagrams, we're trying to get one of the objects on their own without any of the other objects around them. And we're just going to replace, if these objects restrain that original object, so if the other things are stopping it moving somewhere, what we're going to do is we're going to change whatever this is, and we're just going to draw the forces that it can exert on this object. So to start with, we won't know the magnitude of those forces. They're going to have to be big enough to stop it moving. That's what static equilibrium means. So you're going to have a load of imposed forces, then you're going to get some reaction forces, and the reaction forces you get depend on how these secondary objects are interacting with the object you're interested in. Now, it can be a bit of a sticking point sometimes for students when they come across this for the first time. It's pretty easy, but it's just getting your head around what people are talking about. So let's take this first one. Suppose we've got a beam that's supported by a cable or a rope or a chain, anything flexible like that. So you've got a beam supported by a cable. We've kind of talked about this before, but I'll just go through it again just to show you how this works in this case. So let me bring that up, because you'll be able to, what we do here, you'll be able to carry on. So we've got to the other types of support conditions that we haven't done before. And so we've got some B, oops, that's not what I want to do. Sorry, just need to figure out what the heck I'm doing here. Let's start again. So we've got a fixed wall, that's what that's showing. This is attached to the wall, some kind of rope. It's not what we're interested in. What we're interested in is some kind of beam like so. Maybe it's an I-beam, so that's drawing the flanges. Got a hole through it so that we can attach it. And in reality, this would go on for a while, but we just cut it off for the drawing. Okay, so what you do to figure out what the support reactions would be is you just imagine that and think about which direction can it not move in. So where can it not move? So if we think about this one, you're thinking about translations and rotations. So if that was just connected by a cable through a hole, we could move it. Well, certainly the first thing is we could rotate it. So we could rotate it like that. There's nothing to stop that happening. It could just rotate like that. So that means that there's no moment from this connection. If there was a moment, that would resist turning. Okay, so if there was a moment reaction, that moment reaction would stop this thing turning. This one doesn't have a moment reaction because it's just connected at a hole. It's connected at a point, can't exert a moment. Now, then we've got to think, well, could I move it this way? Well, or this way, I'm trying to keep it flat. Not really, but what would happen is if we tried to move it this way, so say we put a force like this, what would happen is that cable would swing up like so. Do you know what I mean? And so it kind of can move in that direction. Similarly, this way, it could swing down on that cable, so the cable would end up here. You know what I mean? But it could swing down that way. So it can go up and down. You got to think, which direction can it not go in? Well, it can't go in the line of action of that cable. It can't go that way. That's tied tight to that. If you tried to go that way, it would just make this cable tighter and tighter. You'd be exerting a larger and larger force. And so for this one, it's the directions it can't move in. That's where there's a force. Now you've got to be careful with this one because it could move this way because it's just a cable, so that cable can go slack, so it could go this way. Okay, so that's the first one. So then what that means is if we were trying to take that support, we're trying to get rid of it because we want a free body diagram. We just think about which direction can it not move in. Well, it can't move. Let me just try and draw it. I'll just try and get the angle right. Sorry, let's just do that. It can't move this way. It's not possible for it to go in this direction. I'm looking at displacement now. I'm not talking about a force. Can't move that way. So that means there must be a force in this direction. And the magnitude of that force will depend on the load you're imposing on this beam. So you're going to be looking for static equilibrium. You're going to try and find this force. Okay, so it can't move in this direction. Therefore, there must be a force in the other direction, and it can only be tension because it's a cable. Okay, otherwise, if this was something solid like a strut or something like that, the force could be either what's the word? Either sign. It could be positive or negative in that direction. But in this case, because it's a cable, it can only be a tension force. Okay, so that's what it's saying here: tension force towards the cable point of fixity. Now, let's have a look at the next one. Just give me a second. There we go. So let me rub this out. So this time what we've got is we have got what is it actually? Smooth surface, is it, with a rolling object? Roller on a smooth surface. So if you've got a smooth surface like this, and you've got a roller on it, oh, didn't want to do that, did I? So first of all, we just want the smooth surface, like so. And then let's move that across a little bit. And then we've got a roller on top of that. Let me just put a point on that and see how we go. Now, if we think about what's that surface doing, what direction is it stopping this roller moving in? Well, the roller can move down this way, so it could roll down that way. It would have no force there. Or it could roll up this, no, ignore gravity, that's a different thing. It could roll up this way. Nothing to stop it rolling that way. There's nothing to stop it flying off this surface in any direction. What is prevented is the roller going into the surface in that direction. That's what's prevented. It can't go into the surface in that direction. And so if we come back to this diagram, what does that mean? Well, it means that the reaction force that you would draw, what angle was that? 36. So 36, 56. It can't go, let me just do a different color for direction. So it can't go this way, it can't go into the surface. That's the direction it can't go. So therefore, the reaction force that you'll get from that surface is in the opposite direction. So it's a reaction force perpendicular to the surface, like so. And it's pretty similar for a frictionless surface. I probably don't need to do that. So if there's no friction here, this block could slide down this way, could go up this way, just ignoring gravity. So someone could push it here and it could go that way. Someone could take it, they could lift it off, like so. What they can't do is push it into this surface. So again, the reaction force is perpendicular to the surface, and this time it's compression only. Both of those are compression only, can't go into tension. Okay, so let's just go back to that ball again. There's nothing joining that ball to the surface. So this force is a compression force only. So if I try and push down, it'll push back up. That's a compression force. There's nothing stopping it coming off that surface. Let's quickly storm through them all. Now, better draw this one. So what if the surface has got friction on it? Just clean this up on both sides. Oh, you can't even see it. Hold on. There we go. So what we've got this time is a surface with friction, and so it's a bumpy surface like that, say. And we've got a little block, and the base of that block is also rough. It's got friction. So let's think what happens this time. Well, the same thing's true. You can't push it into the surface. Sorry about the smudged lines. This was the best pen I could find. And so you can't push it into that surface. So we're going to still have that reaction force perpendicular to the surface. That's going to be there. But we're also going to have, you could push it this way, but because there's, let me do that again. Sorry, guys. I keep forgetting that when you put it on that, you can't see it. So let me start again. We've got some rough surface here. So we can't push that block into the surface, like so. Move it across into a better spot. Can't push it into the surface, so you've got that same reaction force. Now I could push it this way, but there will be a force resisting that, and we're going to look at friction later. That force is limited, it can't get infinitely big. And so it's going to have a force that's resisting you pushing it that way. And what does that mean? Well, that means there's going to be a reaction force the other way. There's going to be a force resisting it. But you could equally say that there's going to be a force the other way, because if you were trying to push it this way in that direction, that would also be resisted. So there'd be a reaction force going the opposite way from the direction of motion because of the friction there. We'll talk a little bit, as I say, we'll talk about friction later. And so if we go to this problem now, this here has two components. This force, or this support condition, there'll be a reaction perpendicular to the surface, like so, and there'll also be a reaction in the other direction. Now, usually you would just draw it in one direction. So you would just say, look, there's going to be a force parallel to the surface as well. And if you went through the calculations and it was actually in the other direction, so say it was that the block was actually getting pulled this way, this is in the other direction, what'll come out is you'll get a negative answer for this. But when you're drawing your free body diagram, you would usually just draw these arrows just in one direction. You wouldn't draw them in both directions. Okay, let's push on to the next one. So we've got a roller support, and they're actually all very similar. So the roller, this is also a roller. This is also a roller. This is a rocker, they call this, a rocker. And so let's have a look at that one. Rub this out. And it's pretty similar to what we just did. With well, it is actually, it's not similar to it. It's the same as what we just did. It's this one up here. Where is it? This one. All you've got here is you've got a circular object on a smooth surface. Same here. This can rotate because this is a free pin, so that can rotate around. So it's also a circular surface, circular object on a smooth surface. It's just a big circular object, and you've only got a part of it. So this could roll so far. And what you would do is, usually these are for thermal expansion, so you just make sure this is big enough to allow for how much the object that you're supporting would expand. But they're all basically the same. So let's just draw that. What have we got here? Let's have a look. It could be tricky. Which one will I do? I might do the rocker. All of them are tricky because they're rolling, but that's okay. Let's just do the rocker. I actually need 3 bits of clear plastic, but that's a bit more than I've got. I've got enough hands to move them all. So you got some kind of rocker in there, it's pinned. 2 seconds, let's start that again. So we've got some smooth surface. I need to show you this. We've got a smooth surface like that. So just showing that it's a solid surface, just draw some lines underneath it. And then what we've got is we've got the one you usually see drawn in the diagrams actually is what I'll do. You usually see this one, they draw it almost like a little triangle with some rollers underneath it. So again for this one, it could roll this way, so there's no reaction force in that direction. Could roll this way, whoops. Could roll the other way, so no reaction force in this direction. Could lift off, so there's no tension, because it could lift off here like that. The one thing it can't do is it can't push into this surface. So it can't push in like that. So again, you've got a reaction perpendicular to the surface. So let me just draw, and that's the same for all of these. So the reaction force you could get out for these, could be like that for that one. This is exactly the same. The reaction force can only go up the way. It can't hold this thing down. It can only go up. And to be honest, there won't be any questions, I don't think, that you would get. You might be asked when would the support lift off or something like that. And you'd know that because that would end up being negative, that if you draw it like that force. So it's got a compressive force normal to the surface. Let's keep going. Pin support now. So let me try and see if I can keep this going. Oh, did I close that? You fool. Just open that up again. Take about, oh, not too bad. I was going to say it'll take about 3 hours to get started again. So pin connection. So that's basically a hole with a bolt through it. So you do a hole in both of the objects and put a bolt through them both. Usually you have if you're holding something down, you have something front and back. But say for this here, so you've got some kind of support like so. This is called a clevis. If you looked at this the other way, so suppose I looked at it that way, it would look something like this. There'd be a support here, and it would have a base plate on it. And then you might have some kind of beam or something with a flange cut off going through here like so. Oops. I have to do that again now. So let me just draw it again. So we've got that. We've got that like so. And then we've got some kind of beam going through it. It's hidden because it's behind. And it could be a big beam, whatever, something like this. And you'd have to cut the flange here to get that on. You'd have to cut that flange off because maybe you're looking at this one this way. It would be an I-beam like that. So you'd need to cut the flange off. And that I-beam, so in the clevis, it would, the web, it's called, that's what the central bit's called. It's called the web of that beam, would sit in between, and you'd have a bolt through like that. Okay, that's a pinned connection. So let's think about this one. Interesting, because it's underneath. Yeah. Let's get rid of the stuff we don't need. That's that one. Okay, so let's think about this one. So in this case, it could rotate that way or that way. So there's no moment resistance in this, just so I can line it up. What I might do is also put a dot on the beam. So there's no moment resistance because it's free to rotate. If it had a moment resistance, it wouldn't be able to rotate like that. We'll get to some with moment resistance in a minute. But it can't move this way, can't move that way, can't move that way, can't move that way, can't move in any of those directions. But we don't draw reactions in every direction. We just usually draw on the X and Y reactions. And they could be in either direction. So it's stopping it going down the way, but it's also stopping it going up the way. So it could be in either direction, but usually we'll just draw on the positive, or we'll draw on the one we think it's going to be, the direction we think it's going to be in. So you just guess to start with. If you're wrong, it's no big deal. You just end up with a negative number at the end of the day. So what does that mean? Well, for this one, so it's restrained from going in any direction, but we could represent any direction just by different combinations of the X and Y components. That's what we've been doing all this time. So say we've got any random vector, say something like this. Well, we can always find an X, a Y component and an X component. And the actual X component would be the same point of application, BFX down here. We can always find any components that would add up to give you that. So we don't have to draw on arrows in every single direction to show it can move nowhere. We just need the two, or we just need those two, the X and Y components. And in this case, it's not free to rotate, so there's no moment component to this, so a couple moment. We've been talking about a couple moments, like this concentrated moment. Getting through it. So let's just get Ladybug back. There he is, there she is. Clean this off. Put the little one on top this time is better. Okay, so the next one, this has got a few different names, this one here. So sometimes it's called encastre. So it's from French, encaster, and just means encased. So it's been encased, but basically you've got some kind of concrete wall, or maybe it's an abutment for a bridge. So that's the big concrete blocks at the end of bridges. And so you've got some bit of concrete, and you've poured the concrete around this beam, so it's completely encased. Another word for that is to say it's built in. Another word for it is to say it's a fixed support. So it's completely held in that position. Or you get similar stuff with just steel work on its own. If you were to weld all round and it's onto something nice and stiff at the back, and weld all round, you'll get a fixed support as well. So let's think about that one. Well, it's pretty trivial, to be honest. So we've got something like this. Let me just show you it, so I'm not just talking to myself. So we've got some kind of wall. We've got this beam. Let's take the welded one, for example. So we've got a beam like this, fixed here, fixed here. We're just cutting the drawing short because I'm lazy. So this time, can't move that way because it's welded on. Can't move that way, it's welded on, or it's encased. Can't move that way because that bottom bit's welded on. Can't move that way because the top bit's welded on. It can't move nowhere, so it can't move anywhere. So again, it's a similar situation. but this time can't move anywhere at all. And so for this one, you don't draw every single direction. We just keep aware that when we're doing this stuff, just a second, that you could get any direction just using the X and Y components. And so we would maybe say there must be a Y, so there must be a Y reaction because it can't move in the Y direction. There must be an X reaction. It could be either tension or compression in this case. Can't pull it off. And so you've got both of those reactions. So you've got an X reaction, a Y reaction. We call that Rx and Ry. I wasn't really doing that before, but this would be Ry. This would be Rx. Doesn't have to be R. It can be whatever you want to call it. But this time we've got an extra condition. We couldn't rotate it either. And that means there's a moment reaction as well, or a moment couple reaction. We'd call that M maybe. And you'll notice I'm drawing it in the positive direction, so anti-clockwise is positive. But you could just draw it in whichever direction you think it's going to be in. And then if you've got it the wrong way around because you guessed wrong, you'll just get a negative answer. Okay, so that one's got a moment reaction as well. Why? Because you can't rotate this. Can't rotate it in either direction, but when you're drawing the forces, just draw it in one direction. If it's in the other direction, you just get a negative answer. Last one. Now, there's more of these, so you can always go on, look in the textbooks or whatever to look at different ones. But by the time you get to about this point, you should be able to figure out what the reactions would be. So what reactions you get for it. This is sliding, so you've basically got a sleeve over the top of a rod. So the rod's running through the middle of it. That's a sleeve, and you've got something connected to it. And we're interested in the thing that's connected to it. That's what we would want to draw the free body diagram of. One thing you should note here, these are not really free body diagrams because I've drawn that support. In fact, let me just, that should not be there. The hole can be there because that's part of the original beam. But in a free body diagram, you should not be drawing the actual supports. Have I done that for the others? I have. That's interesting. So you shouldn't be drawing that because you're just drawing a free body diagram. Similarly here, shouldn't be drawing that surface. We should just be drawing the object that we're interested in for a free body diagram. So let me just get rid of all of those. That's better. Did the right thing for the first one and then got lazy after that. I think I was getting carried away cutting and pasting. And similarly for these ones down here, I can't change those because they're drawings, but you shouldn't be drawing that surface, you shouldn't draw this roller. If you're interested in this thing here, you should just be drawing that on its own. Okay, last one here, let's have a look at that. So what have we got? Let's see if I can actually draw this. So we've got some rod, we've got a sleeve going over the top of it. And show ladybug. There it is. A rod with a sleeve over the top of it. And the thing we're interested in is this thing up here. Who knows what it's attached to? We've cut it off in the drawing. You can't see it. Why am I such a fool? Just draw the rod. And to show you it moving around, I need to draw this bit. So that's the sleeve over the top. That's the object we're interested in, which we've cut off because it's a drawing. Okay, so what can we do this time? Well, it can move that way, so it's not restraining anything in that direction. It can move this way, not restraining anything in that direction, but it can't go that way. It can't move like that, and it can't move like that. It can't move like that either. And also, it kind of depends how long the sleeve is, but it can't rotate like that either, so that's also restrained. So it can't rotate like that. So therefore we can figure out the reactions. The reactions are just forces in the directions or opposite to the directions that it can't move in. So let's go back to here. And really we'd want to get rid of everything but the object we're interested in. So we want to get rid of this stuff inside here, I guess. But I'm just going to get rid of everything. So I'll just leave that on. But you know what I mean. You'd only be drawing the actual object. And so the reactions associated with this force, well, it can't move this way. It's a bit like the frictionless surface, which is what you'd assume for this. There might be some friction on this actually, unless it's well lubricated. And so you're going to have a reaction that way. It could be positive or negative. So it could be, it also stops it going in the other direction. So it's also got a force that way, but you don't draw both of the directions. You just draw one direction and you get a negative answer. And it also prevents rotation. So we also need a moment reaction as well for that one. Okay, so that's those. And now we'll look at moving on a bit further with the rigid body analysis itself and drawing some real free body diagrams.